Well, good evening, everyone. My name is Robert Black. I'm the Planetarium Director. Let me put this to bed. Anyway, good to have you here tonight. This is a big night for us. We've got our North Medford High School Stellar Alumni program tonight. Really happy to host this webinar. I'm here at the, beside the planetarium here at North Medford. I'd like to just tell you a little bit about the format. Our three guest speakers, former students, of course, been asked to give a 20 or so minute talk. We're not timing it exactly. And then be presented with a few questions by our Solar System Ambassador, Mr. Colin White. If everybody would say hello to Colin. Thank you, Colin, for being here tonight. He's gonna, if you have questions for our speakers, we're gonna take a couple of questions after each presentation, and he'll be asking those. So thanks, Colin. Our program tonight is sponsored by, of course, North Medford High School, Science Works Museum, and the Southern Oregon Skywatchers. We're happy to have all of the sponsorship that we have and the support. Our three students are fantastic space scientists. Our first speaker tonight graduated from North Medford in 2010. She went off to the University of Wyoming and got a dual degree in astronomy and physics. That's tough to do. I remember a lot of kids talking about doing it, and very few actually did it. While here at North Medford, I got to mention this. Rachel helped me in the planetarium make plenty of upgrades. I think Rachel single-handedly helped me more with doing improvements. She came at that golden time when I needed some help, and she was very inspirational in helping me. She also did two great projects. Her and her dad took pictures of every constellation and bright star and connected the dots, and I still use some of those, Rachel. Thank you. In the planetarium programs that I still do for the kids. And she filmed it. You guys remember L Cross? I don't know if Dave and some of the Skywatchers are out there. She filmed that Cabeus crater when that impactor hit. I don't think it was 2009, wasn't it? And we were supposed to see the big plume. It just didn't work out that way, did it? But still a great experience. But Rachel went on to the University of Wyoming, got 2 degrees, worked at the Wyoming Infrared Observatory there. Also worked in their planetarium. And went on after her dual degrees to the University of Arizona in Tucson, a great dark city, and where she got her PhD. She worked at the Stewart Observatory and became really great at computational astrophysics, worked with binary stars and can planets orbit, stable orbits around them, and worked out in the Pluto system of the Kuiper Belt. What I want him to just talk, I forgot to mention, she got her PhD last year and now works at Los Alamos National Laboratory. So congratulations on that, Rachel. But I've asked him to kind of give some college career, some kind of ideas that she thinks would help today's kids navigate through college and then career. So with that, if we could give a virtual hand to Dr. Rachel Smallin. So Rachel, it's all yours. Thanks for being here.
Thanks. Did you want to record?
I'm not going to record.
Okay.
But
right.
It's all yours.
All right. Are you seeing my screen?
Mm-hmm.
Perfect. So thank you for inviting me to kick off this event. This is very exciting. So Mr. Black asked 3 of us to come back and inspire the children and then teach them how to be just like us. So, hi, I'm Rachel. Depending on where Zoom put me, I'm somewhere. And I'm a computational astrophysicist. Now, normally when I say this to people, they're like, oh, you must be really smart. And some days I feel smarter than others, but being a computational astrophysicist means that I use simulations and supercomputers to do my research. And the astrophysicist part is I try to understand how the universe works the way it does instead of what's in the universe, like a traditional astronomer might using a telescope. So the first thing that people normally learn about me and my science is that I really like binaries. I was actually rather infamous for it in graduate school. People would always turn, if we were in a talk and somebody said the word binary, and look at me to gauge my reaction. But I actually first encountered binaries in high school during one of the kind of dark sky nights that Mr. Black hosted. So an example of a binary is shown here in this picture. This is Alberia, which is a beautiful blue-gold visual binary in the constellation Cygnus. I didn't know it at the time, but binaries had kind of changed my life. And so in the more scientific sense, a binary is a system of two objects. And these two objects have roughly comparable mass within about a factor of 10 of each other. And they're orbiting a common center of mass. So this means that the point where the gravity of the two bodies tugging on each other cancels out is exterior to the surface of either individual body. So binaries exist in a lot of different places. So I've studied binaries at many different scales, from dwarf planets to planetary systems, all the way up to the scales of star formation and giant molecular clouds. So to give you an idea of how I can think about binaries in different ways, I want to take you through a couple different things that I've thought about. Let's start at the smallest scales and think about Pluto. So sorry, Dad, who I'm pretty sure is in the audience, Pluto is not a planet. Pluto is much too small and minuscule to be kind of a traditional planet like Earth or Jupiter, but it's still fascinating in its own right. Pluto is a dwarf planet that lives in the Kuiper Belt in the outer reaches of our solar system beyond Neptune. But what's most fascinating to me about Pluto is that it's actually a binary. In the 1970s, we discovered this object orbiting Pluto that was named Charon, and for the longest time, Charon was considered to be a moon of Pluto. But with recent measurements, we've discovered that Charon is within that factor of 10 of Pluto's mass. So the center of mass of the system, the place where the gravity cancels out, is actually just outside of Pluto's surface, making Pluto-Charon a binary. Even more interestingly, there are 4 circumbinary moons in this system, and circumbinary moons are moons that orbit not just one planet, but they actually orbit the Pluto-Charon binary as a unit. These moons are Styx, Nix, Kerberos, and Hydra, so if you're up on your Greek mythology, you might notice that all of the names in the Pluto system are related to the Greek underworld. So we think that this moon Charon formed through a very similar mechanism to what would have formed the moon in our own, around our own Earth. So there was probably some giant body that hit Pluto, spewed a bunch of debris into orbit around it, and some of that debris coalesced into Charon. However, not all of that debris would have coalesced into Charon. There would have still been some stuff left in the system that we don't see today. So using simulations, I set out to discover where that debris could have gone, and more so, if we could observe any of it in the solar system still today, because that might let us know something about this collision that formed Pluto, which would then tell us something about the conditions in the very early times of the solar system. So by analyzing simulations like the one I'm showing in this movie, I was able to estimate that we should find within the next 20 or 30 years, given our telescope technology improving, we should find a small population of bright icy bodies somewhere in the Kuiper Belt that came from this collision. So that's pretty cool. As a theorist, I actually made a testable prediction. So beyond just a single dwarf planet, now let's think about the scales of planetary systems and talk a little bit about circumbinary planets. So again, this word circumbinary is coming up, meaning something that orbits a binary. if you've seen the indie cult classic Star Wars, you probably have already encountered a circumbinary system. In this iconic shot of Luke Skywalker watching this double star sunset on Tatooine, we see that because of the proximity of these two stars, Tatooine has to be a circumbinary planet. But these types of planets have moved from science fiction to science fact, and we've discovered about 24 circumbinary planets in our own galaxy today. So these circumbinary planets are incredibly difficult to find, right? We have two stars moving around each other and planets moving around the stars, and everything's just a mess. Everything is moving, and our computer algorithms that we like to use to find planets don't like irregular signals. They like nice, regular, what we call periodic signals. So these circumbinary planets are just hard to find, but they definitely exist, and we think that they're fairly abundant. Add to that the fact that about half of all stars in our galaxy are these binary stars. So there could be a lot of circumbinary planets out there in the universe, perhaps some even hosting life. So I asked a relatively simple question, but one that is subtly complex. I asked, do planetary systems evolve differently if you have a binary star at the center versus a single star? So you're seeing an example of one of my simulations play in this movie. And what I found is that what we call the architectures of these systems, the arrangement of planetary orbits, doesn't really change, right? That's a function of the type of planets in the system, not what they're orbiting around. But instead, what makes a big difference here is how planets that want to be gone from the system leave the system. So as we're seeing here, this green planet interacts with some of the other purple planets in this movie and gets pushed a little bit close to the binary star. But then this binary star just gives that planet a huge kick out of the system, and so it's ejected into interstellar space. And so we're going to watch one of these inner pink planets do the same here in a couple seconds. So, given the fact that I said that about half of all stars in our galaxy are circumbinary planet or are binary stars, and that a substantial fraction of these could have circumbinary planets, and that binary stars kick out more planets than single stars, that means that the free-floating planets that we observe in space, which we have found in space, are perhaps from more binary stars than more single stars, which is really interesting when we want to think about the types of planets that we'll find. So enough about planets. Now let's move up to how we form stars. And, you know, in my opinion, star formation is really kind of this fundamental underpinning to almost all of astronomy. Stars form out of giant clouds of gas in space that we call molecular clouds. And you're seeing in this picture a very famous example of a molecular cloud called the Orion Nebula. So if you're ever out at night in winter with a pair of binoculars, you can look up into Orion's sword and see this for yourself. The Orion Nebula is a fascinating region that we can study in a lot of detail. We see a lot of really cool things going on in it. And as we look across the entire galaxy, we see more and more of these regions in all these different environments. So in this case, if we know how our stars form, we can then estimate an awful lot about what type of planets will form around what types of stars, which has consequences for understanding life in our universe. If we know what stars form, we can estimate what stars will go supernova and when. And it's these supernovae that populate our galaxy with heavy elements like iron and gold. If we know how stars form when they're forming, what types of stars are forming, we can estimate how galaxies will grow and evolve over the entire lifetime of the universe. So really, understanding how stars form really tells us about everything else in astronomy. and binaries do play a critical role in this whole process. But star formation is messy and complicated. We don't have a simple model for what's going on. So my focus for the last few years has been trying to understand how the real gas in the universe relates to what we can observe. Most of our universe is hydrogen gas. In the case of where stars formed, it's what we call molecular hydrogen, so two hydrogen atoms stuck together. But we can't see this molecular hydrogen on Earth. There's just not a good way that we can see what's going on. So instead, we have to use observations of other molecules that hang out with the hydrogen, but aren't exactly the hydrogen. So you can see an example of what I'm talking about here in this movie that I'm showing. On the top, you're seeing the real gas in one of the simulations that I'm using. And on the bottom, you're seeing a simulation of an observation, what we call a synthetic observation. And if you kind of watch these two, the upper panels and the lower panels, you can see that while they look similar, they don't look exactly the same. So it's these subtleties that I'm seeking to understand with my active research right now. So you've now heard a lot about me and what I do. So I fulfilled the first part of the brief to hopefully get you excited about what I do. But then Mr. Black also told us to give you the secrets to our success. So in my case, we have to rewind the clock quite a lot. I graduated 11 years ago from North Medford High School. But if we go back even a little bit farther, when I was entering high school, I always knew that I liked science. I was really into math, but I knew nothing about astronomy. So it was in junior year that I took Mr. Black's astronomy class, fell in love with it. As he said, I started hanging out in the planetarium and helping him do all sorts of stuff. And then I graduated in 2010. So with kind of the single-mindedness of youth, I decided that I was going to be an astronomer, right? I wasn't going to be a physicist. I was going to be an astronomer. So I was looking for only astronomy programs. That, at the time, canceled out all of the Oregon schools because all of them did a physics degree with an astronomy minor, and I was going to be an astronomer. So I ended up going to the University of Wyoming, and that's where my astronomy career really took off. So in September, about 2 weeks after I started the semester, just to set the stage, I was kind of existing as a freshman, right? I was 1,200 miles away from home on my own for the first time, living in the dorms, not, a terribly extroverted person, so I didn't make a lot of friends. And I was kind of missing mom's cooking because I had to eat in the dining hall for 3 meals a day. And then an email popped up. And it said, "Welcome back, Fiesta Lunch." So this was from the Physics and Astronomy Department at the University of Wyoming. And they just wanted to have an event for all of the professors and graduate students and postdocs to get back together, say hi, and kick off the new year. Well, they never said that undergraduates couldn't come. So I showed up, got in line, got my chimichanga, ran off to the corner, sat down, put my head down, and ate this delicious, crunchy chimichanga. And this was the start of my astronomy career. So there was this guy, after I finished eating, who totally bounded up to me with golden retriever energy, kind of introduced himself, said, "Hi, you're one of the new people, right?" And I said, "Yes. I'm a freshman, I'm into astronomy." And he said the words that changed my life. "Do you want to go to the telescope?" Duh, right? Of course I want to go to the telescope. I'm here to do astronomy. Going to the telescope is the entire reason of my existence here at this university. So it turns out that that person who invited me to the telescope was the chair of the physics department, Danny Dale. So he put me in touch with some graduate students who took me to the telescope. They even let me control the telescope, why they let an 18-year-old have sole control over their multi-million-dollar facility? I'll never know, but I managed to not crash the telescope that first night, although I did at least once later. But that really was the genesis of my astronomerness, right? So if I'm going to give you a piece of advice, it would be, don't be afraid to say yes, right? Saying yes to the simple question of, do you want to go to the telescope, really set the course of the rest of my career. So, fast forward over the next year, one of the professors in the astronomy department invited me into his research group, Chip Kobalnicki, and he invited me to do some research on observations of binary stars, of course, right? So I'm just continuing my love of binaries. And Chip was a great mentor. He counseled me on what classes I should take to be successful, allowed me to really get my hands into research and explore a lot of fascinating things about the universe. And he pushed me to share my research with other people by going to conferences. So that brings me to secret number 2. Find good mentors and let them help. These mentors who know the field, know what to do, are really going to be the best people to guide you on your career. And they can provide the advice, support, letters of recommendation that will allow you to go far. So because of all of Chip's support and mentorship, I was able to get a summer internship at the National Radio Astronomy Observatory. I decided that I was going to try research. So go from my research on visual binaries to radio galaxies. Ended up not liking radio astronomy all that much, but I had a great time at the National Radio Astronomy Observatory in Charlottesville. Went back to Wyoming for the semester, did lots of fun research, went to some conferences, did planetarium shows, did outreach events, kind of got involved in a lot of different clubs and stuff on campus. But all of that involvement at UW then let me get another internship the following summer at Kitt Peak National Observatory in Tucson, where I worked on optical observations of galaxies. Figured out I don't really like galaxies, don't really like using Hubble, even though Hubble's very cool, not really my jam for research. So, one thing that I was thinking as I was doing all of these fascinating things with really smart people, I was looking around the room and I realized that I was never really the smartest person in the room. I normally wasn't the person who put in the most hours or did the most work, but I was always the person who was there. So my next piece of advice is you don't need to be the best, right? But you should be involved, because by being involved, people notice you. And it's those people who notice you who will then talk to other people about you. And then your name gets known. And, success breeds success. So by being involved, you can really launch a lot of other parts of your career. Then in May 2014, I did it. I graduated from Wyoming with degrees in physics and astronomy. And around this time, I kind of had an existential crisis. Should I go on to graduate school and get a PhD, right? I had 2 options. I could get a PhD and go become a professor, or I could probably go get a really good industry job and make a lot of money and not have to go to class anymore. For me at the time, the PhD really seemed like the better option. I would have more earning potential in the future if I decided to leave. Graduate degrees always look really good on applications. And I enjoyed astronomy research, so I could do it for another couple of years. So due to that decision, in August 2014, I started graduate school at the University of Arizona. I had decided towards the end of my time in my undergraduate degree that I was tired of staying up all night. I didn't like observing anymore. I wanted sleep. And I also really liked computers. I liked computer programming. So I decided to switch from observational to computational astrophysics. And this was kind of a big decision internally, even if it doesn't seem like a big switch externally, right? I was giving up 4 years of training and confidence in my work to switch to something completely new. This transition was definitely helped by the incredible Dr. Caitlin Crowder, who was my PhD advisor. Remember my number 2 secret of find good mentors. But, that brings me to point number 4. It's okay to change your mind, right? I switched from observational to computational astrophysics. Halfway through my graduate degree, I switched from working on planets to working on stars. And at the end of my graduate degree, I switched from wanting to be a professor to now working at a national lab. So it's okay to change your mind, as long as you gave it your best shot. You shouldn't give up because something's hard, but it is okay to change directions because something's not for you. So you kind of heard what I did from 2014 to 2020. That was all of the research that I told you about, but I'm more than a research robot. I had lots of adventures with friends, traveled all over Europe and America, got married, and lived a rather full and fulfilling life as a human being, in addition to being a researcher. So that brings us to last year. In June of 2020, I defended my PhD. You might tell by the timeline that, my graduation got COVIDed, so I don't have any fun graduation pictures. But this was a real accomplishment, right? It was the culmination of 6 years of my work. I effectively wrote a book, got to send that as Christmas presents to people this year, which is fun. But, after this point, I had to make another decision. What do I do with my life? And for me, what seemed to be best was accepting a position as a Metropolis postdoctoral fellow at Los Alamos National Laboratory in northern New Mexico, where I work now, and I hope to continue working here for the foreseeable future. So with that, I want to flash up my secrets, and I'm happy to take any questions.
Wow. Fantastic story.
Great story. Very, very inspiring, Rachel. Thank you.
That's the hope.
So I get the job of the fun job of asking the questions. Just to remind the audience, if you'd like to ask a question, at the bottom of the screen there's a Q&A button. You just hit that and type in your question. Steve Springer just sent in a message saying, I met your dad. I assume your brains come from your mother's side.
So that would be my Uncle Steve, my mother's younger brother right there. So
wise guy.
Thanks, Uncle Steve.
Yeah. Hey, I have a real question. Yeah. Hey, when you're talking about the Pluto system, or not, actually your binary star systems, and you occasionally will just fling a planet out into interstellar space, I guess. How often does it happen? Would it be that eventually all of those planets would get flung out, or is it just the rare one, would you say, from your simulations?
So I start with a special type of configuration designed to have a lot of planets do things. And so we find that in those types of simulations, about 70% of planets leave. Gotcha. Now, we think that planetary systems form a little bit more sensibly. So that being said, we even think that there have been planets ejected from our own solar system, 1 or 2 back when it was formed, plus tons of small rocks. So within the last couple of years, we've observed 2 chunks of rock from interstellar space that have flown through our solar system. Right. So space is a lot more crowded than we originally thought it was.
Fantastic.
I have a question. So going back to your planetary work, what do you think about Planet 9?
Good question. So, I do Pluto stuff. I do planetary dynamics. Planet 9 was right up my alley. And I actually worked with some people who did other Kuiper Belt stuff, and actually made some of the observations that allowed for the prediction of Planet 9. So everyone in the astronomy community super excited about it when this new Planet 9 came out in about 2015. that being said, it's now 2021, and despite lots of telescope time being used to look for this Planet 9, we haven't found it. So it's becoming vanishingly unlikely that this Planet 9 that was proposed this time exists. But that being said, there's a lot of stuff beyond the Kuiper belt that we simply can't see because it's too far from the sun, so it's not very bright. So it's incredibly likely that there could be planets out there that we can't find with current technology.
Thank you. Rich in the astronomy group asked, in your work today, what programming languages do you use?
So I primarily program in Python, but I also have programs in C, C++, Fortran 77, because some astronomy codes are still from the age of the dinosaurs. But yeah, primarily Python.
Okay, well, Rich is asking because he was a long-term weather forecaster, so he still likes to program in Fortran. So I think that's his interest there. So, Robert, I think I've run out of questions, and I think we're at about time for a changeover, so I'll pass it back to you.
I believe there's actually one more question in the Q&A. Cherry's B says, what do you consider your biggest question that you would like to find out about the universe?
Oh, okay. Yeah, that's a good question.
That's a very good question. Thank you. So I think for me, the biggest open question kind of in my field that I think is really interesting is, how do stars form? Kind of in a very general sense, we have this really hand-wavy way of explaining it, but we have no way of predicting it, right? So in my perfect world, we'd be able to create a model where we can look at something in space and say, we know what this is going to do, and we're just not there yet.
Interesting. All right. Yeah, I thought that's where the UFOs come out, but yeah, no, very good. Thanks, Rachel. That was fantastic. Well, moving along through our stellar graduates, we've got, and by the way, if you're wondering why we're using the order that we are, they're in the order that they accepted my invitation to talk at this webinar tonight. So Rachel was the first to accept, and second up is Shane Bechtel. He graduated in 2016, so he's the kind of the baby of the group. He went off to Arizona State and Tempe, and I think he took my advice. I was really high. I'd spent when I say high on the field trip that I did there for over a week and a half. Met Jim Bell and some of the great astronomers there. And Shane ended up going to Arizona State. And not only did he get a degree in physics, a degree in astrophysics, he got a minor in mathematics. Try that, everybody. He worked, of course, in the Marston Planetarium. So we've got another of our graduates who've worked in the planetarium. He did lots of research. He's spent time at the National Radio Lab. And Shane, when he graduated a few years back, he was the #1. I hope I get this right. He was picked by the faculty of the Earth and Space Science program there at Arizona State as their #1 graduate. He's now working on a PhD at the University of California at Santa Barbara, looking at high redshift quasars. If that's not exciting, I don't know what is. Some of the most energetic things in the universe. So really happy to have Shane with us. He's quite a dynamo. And let's give a virtual welcome to Shane Bechtel. Here he is. Shane, it's all yours.
Perfect. Can you guys hear me all right?
Not yet. Oh, there we go. Something's popping up.
Okay, so you see everything? You can hear me?
Yeah.
Perfect. Just pull laser pointer up. Awesome. All right, everyone. As Mr. Black said, I'm Shane Bechtel, part of the North Medford High School class of 2016. And I really like talking about myself, so this is the perfect opportunity to share my story with you all. Yeah, so just jumping right into it. Obviously, we're going to start with the beginning. As I said, I was a senior in my year of 2015-2016, And at the time, I didn't have the best idea of what I was going to do with my life. I knew that I was heavily interested in science and math, particularly in physics. But within physics, I just didn't really see anything that was like too exciting or too interesting for me to pursue for the rest of my life. That is, of course, until I similarly took a Mr. Black's astronomy course in my senior year. And it's like, I think it was the second class then. I said, this is just so cool. This is exactly what I want to do for the rest of my life. And yeah, never looked back. And Mr. Black was correct in that I was talking to him like very early on in my senior year, and I was saying like, hey, well, I'm looking to colleges. Do you have any recommendations? He says, oh yeah, you should go out to ASU. And so I go out there for one visit day in like late October, and I'm like, oh, this is the place. And so I had committed to going to ASU's School of Earth and Space Exploration by November of my senior year. So I knew well early on that I was going here, and I couldn't have been more excited. The faculty out there are great. Jim Bell, like Mr. Black said, is one of the leaders of the Planetary Society, and he's one of the leaders on the Mars missions. He's now co-leading a space mission called Psyche, and just a lot of different opportunities out there. And so it's been a great experience. And yeah, so I am definitely the youngest one here, and I'm only just finishing my first year in graduate school. So most of this talk will be about my time in ASU. And what better way to start than with the first day? And so here I am right in my dorm room, right after getting dropped off my father, who had just helped me move in everything. And I remember as soon as everything was off the truck and in the room, I remember pushing him out the door saying, all right, Dad, thank you, but your services are no longer required. I'm an independent young man and I don't need you guys anymore. He was smirking as he walked out the door, and little did he know what was to come. I ended up going to sleep that night. I woke up the next morning, started unpacking, and promptly cut off a chunk of my finger. So, man, he did not let me live that down when we met up for lunch that day. Don't worry, I did get better. But besides being just a fun story, I just wanted to highlight that there's really never a point in your life when you stop making dumb, stupid mistakes or ever stop needing to rely on other people for help. And so this was just a really early reminder of that for me. And I've made plenty of mistakes since then. I've continued relying on my father well past the day I told him his service is no longer required. And he still makes fun of me for it to this day. So just a life lesson to learn early on. But now actually getting started with my actual ASU career. My freshman year was mainly spent adjusting to college life. I was really concerned that college would just be a bit too hard for me, even though I had done pretty well in high school. So first year, I was like, all right, just focus on classes. And as soon as I saw that I could start handle it, I was like, all right, well, now let's start reaching out. I took a job at the Mars and Exploration Theater, which is an amazing planetarium. This is a 3D rendering of the universe, and I can freely fly through it with the controls that are right behind my head there. And it's just an amazing experience. You go from the Earth all the way out to the edge of the universe. It's one of the coolest things I've ever seen, and I've seen it like 1,000 times. And I also joined a lot of extracurricular activities. This is the Planetary Society at ASU specifically. And this is an outreach organization, one of a few that I had joined. And this were primarily meant to go out into the greater Phoenix area and bring Earth and space science to the local communities there, many of whom don't really get the chance to learn about it, both children and their parents. I also worked with the Portable Planetarium, which you could take from one location to another, and it's like inflatable, so you can inflate it up, and you'd be able to do a portable planetarium show for students in their gymnasiums at any time of day. So again, just a lot of cool experiences out there. I even co-founded the Star Wars fan club, so I'm really just living up to that nerd description, but it was just a great time. And especially my freshman year, I was like, all right, I want to make time for all of this stuff. And you'll see later on that I kept time for that. I never really had to compromise, but I'll get into that in a bit. Namely, my second year when I actually started doing research. So my first year was mainly just spent acclimating and getting into a bunch of clubs and activities and just sort of finding out what I wanted to do, what I was interested in. Second year where I was like, all right, now it's time to actually start earning my keep, trying to get some research done. So this is the Asu Hera Collaboration, and Hera stands for the Hydrogen Epic of Reionization Array. It's a mouthful, but what it really is just a radio telescope that's being built out in South Africa. You see a handful of the antennas here, and I think they'll have about 350 or so when they're done. So it's a massive project. If you see very closely, actually, these are telephone poles, and this is chicken coop wire. So you can actually do a lot of amazing science for cheap, and you really need to at times when you don't have that much money and you have to build 300 and some telescopes. So it's a really cool project, a lot of great friends. And this here was my primary advisor, Dr. Danny Jacobs. And this was my main mentor, Dr. Adam Beardsley. And so I did a lot of cool work with them. Namely, since the project was still really early on and we only had like 15, 20 telescopes up and running, we were just taking some preliminary images of the night sky and trying to essentially create a pipeline for procedure for how we would then process future images once we were actually at the radio telescope up and running. And sounds sort of interesting, but it's actually a very tedious project. If you look at these two images, for example, they're actually quite interesting in that this is the center of the galaxy here. And we're imaging it with this not even like 10% of the way done telescope. So really cool. But you may not even be able to see it, but they're actually slightly different images. And the way that they were made creates those little differences. And we argued about that for days on end. And it was just very tedious and at times boring, but still was really cool being like behind the scenes of how a telescope was actually like getting started in its very initial phases. So really cool experience. But I didn't just do astrophysics research, actually. I was actually part of a biophysics research lab. This is the Bioman Research Lab. This here was my advisor, Dr. Rizal Hariati. And I mainly went into this lab because I wanted to try and see something that wasn't just pure astrophysics. I wanted to have an experience, just make sure, oh yeah, astrophysics is what I wanted to do. And this research was very interesting, but it's definitely not what I wanted to do. I essentially spent my time working on DNA kinematics. And that's just a fancy way of saying they wanted to essentially see how quickly DNA strands can couple together and then break apart. And essentially my work was just putting together these little samples, taking these samples to the very high-powered microscope, and then imaging them with the Xbox 360 controller. Very fun setup, very cool lab. Definitely not what I was interested in, though. It was good to get that experience, though. And so you might think that now that I've started doing research, 2 research groups, in fact, that I had to give up a lot of those activities that I was doing earlier in my freshman year. But a big lesson that you'll learn is that you can make the time for just about anything if you are motivated enough and you want to do it. For example, I kept doing everything that I was involved with my freshman year, all those clubs, my job, all my courses. I kept up with everything. And I even added on a new activity. I joined the Quidditch team, which if you have not seen it, it looks about as nerdy as it sounds. And I'm running around on a PVC pipe. I got a dodgeball. It was quite the opportunity. And even this, I was able to add on with everything that second year. So if you have the motivation to do stuff and you're really just excited about it and having a fun time doing it, there's always a way to make it work, trust me. And yeah, so after that, I spent the summer at ASU and I continued on with that research from the Hera Collaboration. This time I was working primarily on trying to see how we measure whether or not antennas are working properly. And the main idea here is you see this little color bar. The closer it is to bright yellow, the better an antenna is working. Like that antenna is working great. Closer it is to blue, all these antennas, they're really not working that good. But we didn't really trust this way of measuring the antenna performance. And so what I did was I found a way to summarize it in this neat little visual. And I even made a movie about it as the night went on. And you would see that there's always this really strong like bias towards this very up and down pattern. And that shouldn't be there if it's working properly. I mean, there's no reason for all the working antennas to be just right in this line. You'd expect them to be like all over the place, all randomly. And so seeing that, we knew something was up, and I actually went to a conference to present on it. It was the most boring paper in the world if you were not part of this Hera collaboration, but everyone in it was very interested. And as a result of this paper, we actually ended up down the line just getting rid of that performance tester altogether in favor of a new one. So that was very exciting, being part of actively developing the process in which this antenna would be built and how stuff would be imaged in the future. And I like the idea of saying that, like, because of me, we realized this was just a bad idea and we changed it. So that was just a really cool thing, being a part of it and having an active difference. And so going into my third year, I was continuing with my Hera research. And at this point in time, I had to perform my Barrett honors thesis. So I was part of the Barrett Honors College at ASU. And namely what that required is an additional thesis in addition to my senior thesis, which I'll talk about in a bit here. This honors thesis was a bit dry, you'll see here. So I showed you earlier some images that were made from the actual antennas, like what they were seeing of the night sky. But that's not what we get when we actively collect data from the telescope. The data comes to us in this form, where you have, at every time step that you measure something, you have a whole range of measurements across a frequency space. And we perform a maneuver called a Fourier Transform, which changes this frequency grid to delay modes. And those aren't quite so important. We also average in time, so we get a 2D plot. And the main takeaway here is that the thing that we're trying to measure is way out here away from the center peak. So we don't really care close to the center peak. We care about what's out here. And the hard part about measuring out here is that it's very susceptible to interference and contamination from that interference. Namely, we're talking about radio frequency interference. And you can see in our actual data all these bright up and down straight lines. Those are all satellites communicating to one another. So although we're trying to measure astrophysical phenomenon, these satellite communications are going on overhead, and we're measuring that as well. And that's the reason why it's being built out in the South African desert. You might recognize that 100 megahertz is actually the FM radio band. So if we were right next to a city, we would literally just be listening to music all day long in this entire section, and we would never be able to hear the astrophysical signals we were looking for. So this is a big problem. We mitigate it as much as possible by going out far into the desert, but we wanted to see if we could effectively remove the lingering RFI, the radio frequency interference again. And if we do remove it, will it affect this range of signal out here such that we won't be able to make our measurements? And it's a whole technical thesis paper that even I get bored to read. So the main approximation for it is that this is our measurement, and we want it to be as close to this orange line as possible. And at the very most, it's about 10% off, but the behavior is very similar. And so we took that to be a very positive sign, an idea that at the end of the day, we will be able to remove that radio frequency interference and still measure our signal. So that's great. That's an amazing result. There's only one problem. I just wasn't excited anymore about a lot of the research I was doing. It was all cool. It was all interesting to see behind the scenes. It was just a lot of technical stuff and not too much of the astrophysics I had fallen in love with in Mr. Black's class. And so ending my junior year, I was sort of having a bit of a, not crisis, but just sort of a moment where I was like, I really just had to question if this was actually what I wanted to do. And luckily at that time, I had the best experience I could possibly have. I had applied for that summer multiple internships called REUs, or Research Experience for Undergraduates. So these are different institutions or universities that will offer summer programs where university students can come out and work on research out at their facilities. So I applied to 7 my junior year, and I got accepted into one, the National Radio Astronomy Observatory, which I'll talk about in just a bit here, but I first really quickly want to highlight one other point. So I applied to 7 of these programs, and I only got accepted to 1. And I consider myself extremely fortunate to even have gotten accepted to that one. One thing that you have to really understand at this point, especially as you go on, is you really have to learn to roll with rejections. There's going to always be rejections. You can't get accepted to everything, even if you have the best resume in the world. My year before this, I'd applied to 10 REUs, and I hadn't got accepted to a single one. So I was 1 for 17 at this point, and I couldn't have been happier that I even got that one. And now, maybe there are some people that will be accepted to almost all of them, but you can't really expect that. And you really do have to learn to just sort of take the rejections and not get put down by them. You have to learn to go like, okay, cool, on to the next application. And that's going to be really important later on, especially when you start looking at graduate schools, or many of the students here probably already know this from college applications. But the sooner you can really handle that, the better. But enough of that, a bit of depressing news, but not really. But we're going to look at my time at the NRAO, which was, again, sort of the turning point for me and once again reigniting my passion. So the NRAO stands for the National Radio Astronomy Observatory. It's a nationwide institution where we all get together and just obsess about radio astronomy and radio astrophysics. Hera being a radio telescope, I had a lot of experience with this, and so I was right at home here. I was at the Charlottesville location, which was a part of the University of Virginia. And I was in a program led by Dr. Jim Bratz. He's a great man, and he has even better backhand in tennis. Watch out. This guy is amazing. And at this point, I just want to highlight my advisors in this research. Dr. Bjorn Emmets and Dr. Il-Sang Yoon were the 2 scientists who led me on this research internship. And it's because of them heavily that I got that flame ignited again. They sat down with me. They talked about what I was interested in, what I wanted to do, what I wanted to try. And they formed a research project with me that was very much to my interest. And at every point, they were in constant communications with me. They were constantly saying, like, how are you feeling? How are you feeling about this? What are your ideas on this? How do you want to proceed with this? It didn't just feel like I was just someone sitting in a lab that they were telling to do work. It felt like I was an actual collaborator with them. And I am heavily grateful for them, because without that experience with them, I don't even know if I'd be here today. And so having that opportunity was amazing, and I couldn't be more grateful. But moving on to the actual research that I did. So this is going to take a bit of explaining, but here we see an image, ignore the colors for now, but the black and white is an image of a bunch of galaxies, and they're all tightly clustered in what we call a cluster. So these galaxies are all orbiting around one another. And here now we look at this color, and this is actually measuring the emission coming from carbon in this area. Now, as we expect, almost all the carbon is present around this galaxy, but we see that there's a little bit out here in the middle of nowhere. There's nothing there. We don't see any galaxies or anything, and that's a bit strange. So then we followed up with observations of carbon monoxide, which is a molecular gas. That's a bit heavier. And what we can actually do is we can look at these different lines, and you can really just think about this in the way that this is hot carbon monoxide and this is cold carbon monoxide. Now, all the hot gas is well aligned with that galaxy, but we see that for the colder gas, a lot of it has started to sort of move out into this empty space, which we initially saw. And now what we're inferring from this is that due to all these interactions, these galaxies moving around and around, some of them may come close to each other, they might like brush off a bit of the gas. And this cold gas may have been pulled out into the middle of nowhere, and there's now just sort of a overabundance of this cold molecular gas out in the middle of nowhere. And that might seem boring, you might not really care about that at first, but this cold molecular gas is the building blocks that you need for star formation. And so, excuse me, what this implies is that there may be star formation occurring in this region between the different galaxies. And that's really cool, and it completely changes how one might think about how these clusters evolve over time. If there's star formation occurring between the galaxies, that's very different than galaxies just merging into one giant blob. So that's really cool. And this is where I first got a lot of my inspiration to work on the evolution of astrophysical systems. Seeing how this might change how we affect going from point A to point B was very exciting to me and affected where I ended up going resultingly in my graduate school life. So this was really fun research. Again, this was just the exact thing that I needed to get over my sort of lull and excitement after doing a lot of instrumentation work. And again, I got to go and present on this. This is actually a conference in Hawaii. If you are interested in astronomy, you'll learn that most astronomers take any chance they get to go to Hawaii. They'll use the telescopes as an excuse, but they just want to go to Hawaii. Yeah, it was a great time. And these research internships, I can't emphasize enough, are just amazing opportunities. It's not all just research. You get to go out and have amazing times with these cool people. They took us out to the Green Bank Radio Telescope. You can see me here, scared out of my mind, if the death grip did not indicate that already. And it's just an amazing trip. And this summer was actually the summer of the 50th anniversary of the Apollo 11 mission. So I got to take a train out to DC. I got to take a picture with the Neil Armstrong spacesuit. And this is one of the coolest things I've ever seen. They played a movie recreating the Apollo 11 mission on the Washington Memorial. It was very high definition, and fortunately I can't show the entire thing here because it's like 15 minutes, which would eat up all my time. But if you have any interest, I highly encourage you to go watch on YouTube because it is just beautiful. They even timed up the boot step of Neil Armstrong stepping on the moon with the exact time they stepped on the moon on the actual anniversary. So it was just an amazing experience. But yeah, with that though, sadly summer has to end always. And I went back into my senior year of ASU. Here, I was working on my senior thesis this time, and I decided to try separating myself from instrumentation a bit more, and I went into a more observationally focused one. So essentially, I was using these images that were created by Hubble to do my senior thesis. The main idea here is that this is a region of space where the next great space telescope, James Webb, some people refer to it as the next Hubble, this is an area in the sky where James Webb will always be able to look. There's some areas on the sky where it won't be able to look at certain times of the year. And there's some areas of the sky where there's a lot of foreground stuff going on. So James Webb's trying to look that way at this stuff way out here, and you have blocking stuff in front of it, which means you can't really see it that well. This region has very little foreground for contamination, and it's always accessible, which makes it the prime viewing location for the James Webb Space Telescope. So a lot of astronomers are interested in characterizing it as much as possible. And that's what my senior thesis was part of. I was sort of just working with the galaxies in this field and hoping to characterize them so that we have a better idea of what's actually in this field before James Webb launches, which will be in a very exciting day. And you'll see a lot of cool science immediately coming out the gate once it opens. again, a better research experience, but it wasn't exactly what I was interested in. I still had my heart set on the evolution mindset of getting from point A to point B. So that's what I was sort of thinking of when I went into graduate applications. But before that, I had to actually graduate. And as Mr. Black said, I got a double major in astrophysics and physics. I minored in mathematics, and I was declared the C Dean's Medalist, which is essentially the valedictorian of the school. And you may think that I'm just putting all this up here just to brag, and I admit that might be a little bit of it. But no, I really wanted to highlight how a lot of these should not be regarded as any more than just titles when you're actually applying and you're trying to get a job or continue working in academia if you want to go on to become a professor. So many of these people place too much emphasis on these titles. And I just want to highlight that they're not what's important. Your courses, your research experience, all the extracurriculars you do, those are what's important. Those are what you should focus on. If getting that double major in physics and that minor in math meant that I missed out on a research experience or I didn't have time to do this other cool stuff, then it's not worth it in all honesty, especially if I can take most of the classes anyways. One student I know famously was talking to her advisor about graduating a year late just because they needed to take one more class for the double major in physics, and they told them that it would not matter whatsoever and that they should not do that. So I just wanted to share that little piece of advice because too many people at times sort of get hung up on all of this and try to do so much in regards to getting titles that they don't really get the correct experiences that they should be looking for. So hopefully that made sense. But yeah, having graduated, I then looked on to the next part of my life, and I knew pretty early on that I was applying to graduate schools. And so just trying to speed up a bit because I don't want to take too long, but I ended up getting accepted to 3. Again, just to highlight, I applied to 3 out of 10, and getting up to 3 was incredibly amazing to me. I barely thought I'd get 1, let alone 2 or 3. But yes, this was incredibly fortunate for me. I was very happy. And if you've been paying attention to my slides, you might be able to infer that I ended up going to the UC Santa Barbara. And that's where I am currently. This is me and my little brother standing outside the front archway of the University of California, Santa Barbara. And it was very funny. I actually sent him a message because he's currently an undergraduate here now. He actually graduated 2 years ago from North, Jake Bechdel, if any of you know him. But he's currently an undergraduate here now. And so when I first started considering applying to UC Santa Barbara, I sent him a text going, hey, is it all right if I do this? I don't want to feel like I'm invading your space or anything. And luckily he gave me his blessing, and I've been entirely grateful for that. Yeah, so I'm currently a member of the Department of Physics. We've made a lot of cool people already. We've gone to do a lot of cool things. This was taken at an ostrich farm. Didn't even know they had those here, but and just want to highlight that these are very important opportunities, regardless of whether you go to college, whether you go to graduate school, whatever. It's very important that you take these opportunities and you get this chance to hang out with people and see cool things. And with that, though, I'm going to end up talking about my research now with, or for the foreseeable future at least. I'm now a part of the Enigma research group. It's led by Dr. Joseph Hanawi here. I wish I had a better group photo, but sadly, I've not met almost any of these people in person. I've met Dr. Joe and no one else in person. Dang you, COVID. Hopefully I get to see them in the near future, though. Without further ado, I want to really quickly rush through what I'm actually interested in doing and what I'll be doing with the Enigma research group in the future. So I consider myself to be a historian with larger time periods. And this is not meant to be any disrespect towards historians, but what I mean by that is if you were to take the entire cosmic universe, the entire timeline of the universe, and shrink it down into the shape of a year so that the Big Bang happens at January 1st, midnight, and the current day happens at December 31st, 11:59 p.m., then you could see that the entirety of human civilization exists solely within the last day. So less than 365th of the entire history of the universe has had humanity in it. And if you're interested in the entire evolution of the universe, going from point A to point B, I mean, as current as it is to as recent as the most current day, then you need to know all 365 of those days pretty well. And that's what my goal is. And that's the dream that I have of helping contribute to in science. So this is a more traditional picture of the cosmic timeline, starting with the Big Bang and ending with where we are today. And we're going to take a quicker look at the beginning of it because that's particularly where I'm more interested. Here we have the cosmic Big Bang, And immediately after, everything is very hot gas, particularly it's all hot hydrogen gas. It's also something that we call ionized, it's called ionized hydrogen gas. So when I say ionized, and you don't really need to worry about this too much, but here's a hydrogen proton, or a proton and an electron forming a hydrogen atom. And when that atom gets energized, say some light, or it bumps into another one, that electron gets sent flying off. This is called an ionized hydrogen. And it's not too important. I'm going to try and speed up just a bit here, but eventually, after the Big Bang, all the gas is really hot and ionized, but the gas starts cooling down until you get so cold that everything's moving really slowly and you can't really excite anything anymore. And so all those electrons go all the way back to their hydrogens and everything recombines to form neutral hydrogen. Now, obviously the universe doesn't end that way though, because if it did, we all just be here in this screen of black nothingness, but that's not true. We look out into the sky and we see beautiful stars and galaxies. And to paraphrase one of my favorite movies, the night is darkest just before the cosmic dawn. And so you see that at some point, what actually happens is you form the very first stars, and those stars go on to form galaxies, and those galaxies form the amazing structures that we see in the universe today. So all this hydrogen gas, while it's very cold and not doing much, it's slowly being drawn together through gravity. And as you get more and more of it, eventually you're able to form the first stars. They get so hot that they get so large and massive that they start doing nuclear fusion, which is what stars do. And so here you have these giant, hot, massive stars in the middle of this really cold universe, surrounded by a bunch of cold gas. And what it immediately starts doing is shining out light, heating up its surrounding environment. It also starts reionizing it. So that same process that happened at the beginning of the universe is now happening again. And as you go, you start forming more and more stars, more galaxies. You start reionizing more and more of the universe until you get to the modern universe today with the Milky Way with us in it. And today, the universe is almost completely ionized. So we call this the Epic of Reionization. And again, just relating it back, this is about getting from point A to point B. And this is the in-between that we're interested in. There's a really cool simulation that shows us off particularly well. And if I can get it to play, there we go. So here you have a universe full of a bunch of stars that start ionizing their surrounding space. So all this dark blackness is just the neutral hydrogen gas, and the stars are the areas ionizing around them are these little blue regions. And you see, you start off very small for you, just a few ionized regions all around. And then as you keep going and going, all these regions start to merge. Stars that are right next to each other merge very quickly. Stars that are further away merge a bit later. It's a very patchy progress. And you see that there's still lots of dark neutral hydrogen everywhere. And it's just very cloudy and it's very uneven. But eventually over time, you can see that more and more the ionized regions overlap. And eventually you get it so that almost all the dark neutral hydrogen has been ionized. And so that's really the process that I'm interested in. But what do I actually study? Well, we're very interested in the sources of these reionization. So it can be stars, it can also be galaxies. It can also be something that we call quasars. So these quasars are supermassive black holes that we find at the center of some galaxies. Now, these supermassive black holes are very distinct as they pull in a lot of gas and dust surrounding them. They're so gravitationally strong that everything around them starts swirling in faster and faster. And they're so massive that they're pulling in so much that this gas and dust, you can think of causing friction against one another, where they start colliding with one another and start getting really hot and energetic. And that releases light. And this light is enough to outshine its entire galaxy. So we look at this galaxy, we only see a single dot, and that's just because the black hole is outshining them all. It's pretty ironic. And if you imagine, if you can outshine an entire galaxy because you're emitting so much energy, that can ionize or heat up a large portion of the universe very quickly. So we have these three different sources of reionization. And as you might be able to infer, the quasars are what I'm particularly interested in, as well as the group at the Enigma Research Group. So just to summarize, we have the timeline. We know a lot about the beginning because we have pretty good measurements. We know a lot about the current day because we're able to look around and see our immediate surroundings. But it's actually really hard to know about this middle ground. There's a reason it's called the cosmic dark ages, not just because it's quite dark, because like the real dark ages, we don't know that much, and we'd like to fill in the gap very much so. So learning about these different sources of reionization, learning about this process will all just help complete this timeline. And that's sort of my goal in astrophysics and what I hope to contribute to the community before my time is done. But that's just about everything. I went horrendously over time, and I apologize for that. But if you would like to know more, please message me at Bechdel@ucsb.edu. I'm happy to talk about everything. And yeah, like I said, I went over. So let's get to questions
Thank you.
if there's
Go
time,
ahead,
or we
Robert.
can just run.
No, I was just going to say before we get to the questions, it's amazing. It was just over 100 years ago that we were debating whether or not there were, any galaxies beyond the Milky Way. So that's amazing. I could talk about this stuff forever. Are there any questions there?
Well, there was a question I didn't get a chance to ask Rachel because it came in a little later. And the question was, do you regret anything? But I would rephrase the question and say, well, if you had your time again, would you do anything different to what you've done?
This all assumes
Shane answer that.
Yeah.
So that was the question to Shane. But Rachel, I'm going to ask Rachel the same question. So why don't you go first, Shane?
Yeah, so I think I'm grateful for all the opportunities of sort of figuring out what exactly I was interested in. I mean, obviously, it would have been great if I sort of just got lucky and nailed the nail on the head the first shot and went to a experiment that I was immediately invested in and could do that for the rest of my time. But I was really grateful that I had the opportunities regardless to trial and error it through and then find that field that I was just so invested in that I can spend the rest of my time doing. That said, again, would have liked if it had been happening a bit earlier, just because I could have gotten started earlier, and who wouldn't want that?
But so the message really is, but sometimes you have to find out what you don't like before you find what you do like.
Right.
Rachel, why? The question was for you. Is there anything you would do different?
So, I was kind of thinking about this. So coming out of high school, I totally had private school Ivy League aspirations, but I didn't have an Ivy League budget, right? So I was actually really bitter when I went to University of Wyoming for about my first 3 or 4 months because I was like, oh, I'm better than this, right? I'm going to a state school, oh my gosh. But it was actually the best decision that I could have ever made in my life, right? Being at a smaller school, I got a lot more personalized attention. There was a lot less competition. So I was really able to shine and be a big fish in a small pond, and that led to success. So, right, it's yes, I kind of regret things that happen, or, in the moment I would do things differently, but every single decision that I've made has ended up being a positive in the long run. So I've been very fortunate that way. So it's that sort of thing of I can look back and see points where it's oh, I should have worded that statement differently, or I should have not gone to the park and actually written the paper that I was supposed to be writing or something. But I'm very happy with my life right now, so really no regrets.
Thanks, Rachel. But going back to Shane a second, so talk about doing things differently, but Rachel's sort of given some things that she feels have enabled her to be successful. Shane, what do you think are the key things to be successful? Giving advice to, say, Mr. Black's students now, what would your advice be?
Going off the theme of the last question, it's not being afraid to make those mistakes, and really as much as I was sort of joking about it, or not joking about it, but you can't be too afraid to waste your time by trying stuff that may or may not be exciting for you. It's always worth it to go out and take those interests and try them. Like my time with the Biophysics Research Group, I didn't really think that I was going to be too invested in it, but it was still something that I wanted to try that was distinct enough from my field, but still applicable to everything that I was working on and learning, that I could see it and I could compare it to something that I was doing with the Hera Research Group. And so just really, it broke me out of my mold and allowed to see my field from an outside perspective, if that made sense. And that really just allowed me to get a better understanding of what I was actually interested in and that I was interested in it.
Yeah.
Right. Thank you.
Wouldn't you agree that experience you got with the chicken wire radio telescopes allowed you to get the National Radio, Observatory internship? You know what I mean? Even if it wasn't your thing, I think that's important for kids to know.
Yep, you never know what's going to be beneficial.
There. Right. Fantastic.
So just a reminder to the audience, if you want to ask questions as we go along, please enter it in Q&A. But I'm going to hand back to Robert to introduce our third speaker.
All right. Well, I am holding right here a rocket that Matt and his high school group made for the Team America Rocketry Challenge. You can see that Matt Hepper right there signed this. So when we've got a real rocket scientist here, and it's kind of nice to finish with him. It's obviously really late where he is in Indiana, so we had to keep him up and let him talk. But I just got to tell you, I have a lot of fond memories of Matt. He was the first Team America Rocketry Challenge student here from North Medford, and his team did fantastic. They had some really perfect. We've looked at them in class just this year. You guys had some perfect launches. You just killed your astronauts. You can't kill astronauts and win the competition. But Matt went on from North Medford High School in 2014 to, I think he went to Washington for a little bit, but then came to Oregon State, fit right in as a mechanical engineer, joined their rocket team. They competed. They're very successful at the, the Spaceport America Rocketry Challenge in New Mexico. That's an amazing facility too. I hope it gets used more. But anyway, his experience there at Oregon State and graduated got him into Purdue, where he's working at the Zucro lab. Oh, wow. That's a storied place. Correct me if I'm wrong, Matt, but it's the biggest educational rocket combustion facility in the world. Is that correct in saying that?
Yeah.
Yeah. So he's living the dream. And I've got to tell you this before I just hand it right over to Matt. When I'm doing a planetarium show, if I ask, who wants to be an astronaut to a group of first or third or fifth graders, every hand goes up and I say, who wants to be a rocket scientist? I'm telling you, there's just as many rocket scientists out there as there are astronauts. So you're living a lot of people's dreams. So congratulations. And Matt Hepper, here he is at Purdue. It's all yours.
All righty. Everybody see that, hopefully? All right, so yeah, as I said before, my name is Matt, and my talk will be of a similar format. I'll sort of discuss my path, and then I'll talk about, or give some advice, let's say. So I think Mr. Black covered all this, but yeah, so I graduated in 2014 from North Medford, and then I went to, I did go to University of Washington my freshman year. I'll talk about that later, but came back to Oregon, got my BS in mechanical engineering in 2018, and then now I work at the Zucro Labs at Purdue for my PhD and master's. So yeah, as we just talked about, this facility that I work at, which is all of these buildings in the picture, is the largest academic propulsion lab in the world. We can test any type of rocket engine that you can think of. We test jet engines, gas turbines, experimental propulsion devices, and even explosives, believe it or not. So yeah, this is really a state-of-the-art facility that even rivals many other labs, even outside of academia. So I know you're probably wondering, how did I get here? Well, at the highest level, let's say, 4 things that it boils down to. First, a lot of great teachers and mentors that I have to help guide me through school and all the jobs and stuff like that. Definitely my family, very helpful. And also my sister influenced me a lot about, when I was really young, about getting my schoolwork done. So that sort of kick-started everything. It took a lot of work, a lot of dedication, but that's what it takes to do this sort of thing. And you got to try and try again. So yeah, so I guess to get into a little bit more detail about what I've done, I really began developing my technical skills my freshman year in high school in Mr. Christofferson's classes, where I learned a lot about technical and architectural drafting, robotics, 3D printing, woodworking, all this stuff, very hands-on stuff. And I was very fond of that. It was very exciting to do all those things. And then I also competed in what's called Skills USA, which is sort of a state level competition, or I guess it's a national competition. But so you go to Portland and then you compete in different areas related to technical drafting, robotics, all this stuff. And I did pretty well. and I competed in architectural drafting, and it was fun. I enjoyed my time, but you know, it sort of distracted me from the rocketry side of things in my life. I had always had an interest in rockets, but I guess after doing all these things that I got distracted and the rocketry side of things moved to the back burner. But then I took Mr. Black's astronomy course my junior year. I sort of realized that, you know, I had to do something space related, and that this architectural thing, not for me. And so I decided on engineering sometime my junior year. I forget when exactly, but it was really, you know, I was kind of thinking, should I do like astronomy, astrophysics, stuff like that? But I was a very hands-on person. I like to hold things that I make, you know, play with Legos when I was a kid. So engineering was definitely for me. And then my senior year, as we talked about, I competed in the Team America Rocket Challenge, which is a sort of a high school and middle school competition to launch 2 eggs to about 800 feet and bring them back alive. And it was a good time. I learned a lot about sort of amateur rocketry, and yeah, it was a good experience. That's a picture of myself and my 2 team members holding, I think, the 3rd iteration of our rocket. So moving on, yeah, as I said, I actually attended the University of Washington to study aerospace engineering, but I sort of realized that probably not the best choice for me, so I left to actually attend OSU to study mechanical engineering. And I was a bit bummed. I was like, oh, you know, OSU doesn't really have an aerospace program, but it didn't really matter because I found that OSU has rocketry clubs that I didn't know about, and so I started working with them pretty much immediately when I arrived at OSU, and it really consumed all of my time, my free time, and yeah, so I that was pretty much my second, or my job, I guess, when I was a sophomore and junior. And then all that involvement in the club really landed me a job as an undergrad research assistant in a university lab at OSU, and as well as an internship later on. And then for my senior capstone project at OSU, I built a few solid rocket motors, which I'll show some videos of. And the way that these projects are structured at OSU is that the seniors are in charge of everything, and all the underclassmen can help out when they need it, but the seniors take the reins, and so that's what I did when I was a senior. And then I enrolled into Purdue University for my PhD in mechanical engineering. So I just want to show off some of these videos of my time at OSU. This is during my senior year, so this was about March of 2018, I believe, and we've done a bunch of tests, smaller scale tests, but this is our first full-size test. And so we got to the Corvallis Airport and bolted to the ground. But to give some sense of scale, this aluminum tube is the rocket motor, which is about 5 inches in diameter and approximately 3 feet long. And it's a solid motor. And so this is slowed down slightly. I think it was recorded with an iPhone or something like this. But yeah, so we're burning it, everything's fine, but then the plume starts to get a bit bigger, and then it explodes tragically. I look back at it now, and it's kind of funny, but I was not very happy on that day. And then we also recorded it, the same test, but with a high-speed camera at 10,000 frames per second. I'm going to skip through this. This is a bit long, but this is sort of the startup procedure. And you can see the igniter get shot out right here. And the plume, to somebody who's in this field, this plume looks really good, but it starts to get much, much brighter, which is an issue, let's say. And then actually we have the camera look at a mirror, which is looking at the rocket. And so when it explodes, you actually see the shockwave affect the mirror because it sort of warps the image, which is really cool to look at. Right there, you can see the image is getting all warped. So this is what it looks like, or what it looked like after. There's a bit of a hole inside. Not really what we're looking for, but we tried again. This was about 3 weeks later, same spot. yeah. This is also slowed down slightly, and that one also exploded for a different reason, but I won't get into why. So then what do? You try again. And this one is actually a little bit shorter. We're trying to save money, but whoops. So this actually worked. We were very happy. It took about 2 months of testing to get to this point, but after this test, we were confident that the full scale size engine would work, and so we tested the full size motor once again, and this is what the test video looks like. It's a bit washed out, but you can see the plume up here. Produced about 1,000 pounds of thrust for about 5 seconds, and that's enough to take a rocket to 30,000 feet, which is what the competition was for this year, the Spaceport America Cup. And so we had a test launch. We drove out to Brothers, Oregon, which is about an hour east of Bend on your way to Burns. And this is our rocket. The motor goes about from here all the way almost to the midpoint right here, almost 4 feet long. And I have a video of the launch. It's kind of hard to see, but there's a rail sitting right here. We're about 1,000 feet away, but you should be able to catch it. No audio, by the way, if you're wondering. So yeah, we hit like 27,000, I think, on the way up, which is a little bit short, and we pulled 10 Gs off the pad, which is about what we expected. So that worked, and we recovered it, and everything was fine, and everyone was very happy. A lot of long nights to get to this point. So then about a month later, we drove to I forgot about this. So this is the same test launch, but viewed from a drone. It's pretty fast, but it's pretty cool visual. So yeah, I think our top speed was like 1,200 miles an hour. I forget. But yeah, then we drove to New Mexico for the competition. This is like the only video that exists of our launch for some reason. But you can't see it from here, but there's some shrubbery in the way. But the launch rail is approximately here, and it's going to take off in about 1 second after the video starts. So you can see that the smoke trail actually stopped, and that's because one of the fasteners in our motor failed and basically ejected all of the propellant out the back. And you can see, coming up here, you can see this streak right here is actually a propellant grain that's burning and falling to the ground. But we completely shredded almost half the rocket, which is really sad. But it was definitely one of the greatest experiences that I've ever taken part of, and I would definitely do the project again in a heartbeat. Like, it was a lot of fun, and I had a lot of great team members. So and that was all at Oregon State, right in Corvallis. And then I'll sort of talk about what I do now. A lot of my research is sort of not in the public domain, so I can't really talk about it. But there are a few things that I will discuss now. And I get this question a lot from parents and other friends, and they're like, oh, what do you do exactly? I'm like, well, sometimes I don't even know the answer to that, but hopefully I can illustrate what I do. So I work on what's called a rotating detonation engine, and I'm sure everyone's wondering what that is. But essentially, it's a type of engine that uses supersonic waves that travel around a circle to produce thrust. And it's a relatively new type of propulsion device that, you know, a lot of people are interested in for numerous reasons, but particularly for me, for orbital launch vehicles, is due to the increased efficiency over traditional rocket engines. And so, you know, companies will dump millions of dollars into R&D to improve a rocket engine 1% efficiency, like improve by 1%. And so with RDEs, we're talking about, you know, 10, 15%. And so you can imagine people are like drooling over the fact that this is a huge deal. But it's never been, no one's ever flown one of these before, but, you know, maybe it'll happen in the next 20 years, something like that. I don't know. But that's what I work on. And so for orbital vehicles, the efficiency really matters because you can launch heavier payloads for a given amount of fuel, let's say. And so you could launch a heavier space telescope with more mirrors if you want for the same price, let's say. That's what everybody is wanting to do with these engines. To give you a visualization of what's going on, I have this video of a simulation. And so there's this detonation wave that travels around this annulus with the fuel coming in the bottom, and then the exhaust is on top, and that produces thrust. And so this is at my lab at Purdue. We have really state-of-the-art facilities, to be honest. And this is a really short video. You might miss it, but this is what we're looking at right here. So that was it. Not much to see, but and then the picture on the right is an RD with a glass body, actually, and so we can see inside of it. And you know, in my lab we use a lot of lasers to make our measurements, which is a whole complicated thing that I won't talk about. But the optical access of this allows us to make measurements that would be impossible otherwise. And so you know, we need to make these really high fidelity measurements in order to fully understand what's going on inside of these things before anybody attempts to fly them. Let's see. So now that I've talked about that and shown you that the path that I've gone, I'll talk about sort of some advice and, you know, retrospective stuff. Hopefully it's useful for prospective students or even people that are planning on attending in the fall. So number one thing I would say is if you want to work in the aerospace sector, you do not need an aerospace degree by any means. You know, having an engineering degree is preferred, but even physics majors can change careers if they so choose. And every engineering major really has a role to play if they choose to pursue that. You know, electrical, mechanical, industrial, even civil, really. So it all matters. But having said that, if you want to pursue an engineering degree at a university, you know, attending Oregon State or the Oregon Institute of Technology are both great choices, and there's no reason for you to spend a bunch of money going to a different school out of state. I mean, the education I got at Oregon State is really great, and I had a lot of great opportunities there that I might not even had at the University of Washington. So speaking of the University of Washington, one thing that they don't really tell you that I figured out sort of the hard way is that even after you get into UW, you know, they require additional applications for applying to your major. And so you'll apply as a freshman, you'll get in, and then you show up and they're like, oh yeah, by the way, in 2 years, when you're a sophomore, you're going to apply to the major you want to be in. So you'll apply to mechanical engineering, you apply to aerospace engineering. And so I was like, so you're telling me there's a chance that I'm not going to study what I want to study? And they're like, yeah. And I was like, okay, goodbye. And so I left to go to OSU, where they're just like, oh yeah, if you have a 2.9 GPA, you can study whatever major you want. I was like, okay, sounds good. So that's what I did. Great decision. I wish I would have done it straight away, but oh well. Some more advice. I would definitely take a handful of AP or dual, the SOU college credit that I think hopefully is to offer that. But I would try to do that. The AP exams are not always the best thing. So, you know, if you take AP calculus and you basically need a 5 on the test for it to transfer to Oregon State. I think maybe a 4. But stuff like that. It's not always perfect. And, you know, you'll definitely save money and time, which is always great, especially if you're going out of state. But your results will vary with, you know, various schools. And so not every school will accept SOU credit that you earned in high school, let's say. But OSU definitely does. I know for a fact. I definitely advise those of you to apply to scholarships to help pay for school. College is very expensive, and definitely would advise applying to as many scholarship programs as you can. And many schools offer sort of automatic scholarship programs. I mean, you still have to apply technically, but it's not, you know, you don't have to do a whole separate application. You just have to like submit your name, so to speak. So like Oregon State, for example, has a 2 scholarships they offer automatically. I think if you have a 3.8 GPA, 3.85 in high school, you're automatically admitted to OSU. I think if you have a 3.5 and you apply in high school and you apply to OSU, your name is already on the list somehow, and they send you an email in like 4 hours, like congratulations. But speaking of scholarships, so 3.85, they give you like $10,000 a year, and if it's 3.4, they give you $5,000. Obviously, there's many more external awards that you can apply for. And also consider the cost of living when you decide on a school, because Seattle is definitely more expensive than living in Corvallis by a long shot. And so it's not really something that I thought about or even understood when I was 18, but hopefully you'll be more careful than I did, or I was. So this section pertains mostly to engineering folks. I don't really know how this world works for non-engineer folks, but I would definitely recommend joining a club. Definitely join like a club that's relevant to your major, let's say. So if you're doing mechanical engineering, Oregon State has a lot of clubs you can join. So there's a Formula SA racing team where you basically build a race car, like a formula car, and you race it every year. And they also build like an off-road style car. And then there's a Mars Rover Robotics Challenge, which is a national competition. You go to Utah, it's really exciting. And then obviously there's rocketry and there's jet propulsion, helicopters, all at Oregon State. And I would definitely recommend joining one of these clubs. And, even if you don't do that, maybe join a club that's not related, that's a purely recreational. So at OSU, there's like a bouldering club, like for rock climbing. So stuff like that is very useful. And, speaking of these clubs, having a great GPA in college isn't everything, especially in engineering. So, many recruiters prefer that students have technical hands-on experience in these clubs and would rather see that than them having a 4.0. And that really matters, to be honest. And, having experience in a club like really sets yourself apart to somebody that doesn't. And it really helps with getting internships, and I would recommend to apply to as many as you possibly can. The internship game is honestly brutal. It's a brutal truth, but many people that I know, they've applied to like triple digits of internships, and they'll maybe get 4 interviews, and that's just the way it is, because it's all like your resume is filtered by a computer, and it's just horrible. But you really have to shoot a shotgun to land one of these things, or unless you know somebody. Networking is important, but you really just have to apply to as many as you possibly can. And the last thing I'll say is don't worry about getting it right when you start. You can definitely always change careers, even as Rachel said, switch majors, switch fields of expertise. It doesn't really matter. And I've met an astronaut who said, I had this when I was a sophomore, and I had the same woes. It's like, oh, she doesn't have aerospace. What do I do? She's like, well, I'm an astronaut, and she got her degree in optical engineering, which may or may not be relevant. I'm not sure, but I was like, oh, well, that definitely changes everything. So, yeah, I hope this was helpful for prospective people and was entertaining at least. So I'll take any questions.
Wow. Fantastic. Well, of course, I have at least one. Those are all. It seems like there's some unifying themes amongst all 3 of our students today. But I was just wondering, in your Rocket Club experience, what did you guys do for funding? I remember how broke I was, and if somebody said, "Hey, we need to get a few hundred pounds of rocket fuel," I'm not sure. Did you get support from the faculty? And
yes. So that's actually I'm glad you brought that up, actually, because a lot of schools. Well, I'm going to say 2 things. First, yes, we did have backing from the faculty. So one of the advisors, Dr. Squires, she retired. She was retired, I guess. I don't know. She was teaching, and she had taught at a lot of universities before this, and this was her retirement. You know, that's the type of person she was. And so she didn't perform research like most professors. And so, but she was still allocated money for her research that never occurred. And so she just dumped all that money straight into the rocketry club. And so all the money that we used for rockets was directly from her research accounts, basically. And we also did get some donations. So if you go to our website, osuaiaa.com, you can see all our sponsors. We get money from like, Blue Origin, SpaceX, or materials too. So, direct material donations, stuff
So,
like that.
so when the rocket blows up, you guys aren't out of your lunch money. That's right.
Yeah,
That's good.
I mean, some money comes out of our pockets, like when we're traveling,
Mm-hmm.
Sometimes you have to spot yourself. So,
Right.
So I have a question. So we've tended to sort of look back of how you got to where you are, but if I had to say to you, where would you like to be in 10 years' time? Or haven't you thought that far ahead?
I don't know. Got to get this PhD done first.
Yeah.
But I don't know. My answer to that question has changed a lot. I don't, I know Rachel's in the academia space still. I don't know if that's really for me. I don't know how engineering compares with other disciplines, but publishing papers, not really my thing. So like, I guess I'm not the best scientist, and I'm more of like, and so like in grad school, you're doing the science and the engineering at the same time. And I don't really like the science so much.
Yeah.
If that makes sense.
That's an important point. I think that if I look at, I do a lot of work at Science Works, and so people there, some of them are scientists and some are engineers, and their interests are different. But the two combined work very well. I mean, like if you look at somewhere like JPL, and it comes back to the point you made, you don't have to have a degree in astrophysics to go into this field. And so if you go to JPL, that they have scientists, they have engineers across many different disciplines. And yeah. I think you're right. I think sometimes you have to learn what you don't like. One of the things I was going to thank Robert for organizing this before we finished, and really to thank him. One message that's coming across here is that mentors matter enormously. And I think Robert's an incredible mentor to his students. And I think the three of you look back to that point. If I look back to when I started, I had a physics teacher, and really it was him that motivated me to do a degree in electronics. As it happens, I went into software, but electronics has always been an interesting line. So I think you learn as you go along, and it's okay to change your mind. And but the key thing is that mentoring is so fundamental. And I'd really like to thank Robert on behalf of everybody listening for the work he puts in, because I think mentors are fundamental to really the next generation and the generation after that. So I don't see any more questions there. And I think we're about out of time. Speaking for myself, I'd like to thank all three of you. I found it inspiring. I always really enjoy working with you guys, or guys like you, because it keeps me going in life. And so I'd like to thank all three of you for being so inspiring. And thank you to Robert. And I wish Robert's students well. I'm sure they're going to follow in the paths of these three folks. So thank you, and I'll hand back to Robert.
Yeah, thank you. Thanks, Colin, for helping out tonight. Yeah, it really is nice to have a group. And by the way, just with the mentoring, I've done a lot of mentoring, but I've also got 5 or 6 people that are just right over here helping me out. So it takes a big group to educate everybody. Hey guys, thanks you so much. It's great to catch up. It's great to hear what you're doing. I don't want to start weeping or anything. I'm not that old yet, but maybe
I am.
Maybe in 10 years or so. But it's really.
Well, I'll be honest with you, Rachel. I felt quite emotional listening to Rachel. I was like, yes.
That's fantastic. But once again, thanks for thanks for volunteering, and always stay in touch. The fact that I can tell my students that you guys sat in these desks, you're in that planetarium, you're in that observatory, that means a lot. So thanks very much. So thanks for everybody who joined us. I did ask somebody, I didn't record it because occasionally around here when you record something, the whole system crashes, but I did ask somebody to record the event. So if that all worked out, I'll share that link with everybody. And I'm hoping that it did. All right. Anything else? Anybody want the last word? Want to see this rocket again? Good job. All right, guys. Thanks a lot.
Take care, everybody.
Bye.
Bye.
Take care.